Thank you for coming to my defense. My name is Jeremy Castagno. The title of my work is Mapping in Real-Time Navigation with Application to Small UAS Urgent Landing. Just a second, I can get this thing to work. Yes, okay. So small unmanned aircraft systems are expected to increase in low altitude airspace, and they're being proposed to use for package delivery, monitoring assets, inspections, and even entertainment. For example, the New York Fire Department is proposing UAS for monitoring fires, police departments for airborne support, and even the Amazon Prime is proposing them for package delivery. Cities are now becoming a primary location for their use. However, there's some large safety concerns of ensuring SUAS have robust urgent landing capabilities. Now, this includes landing site selection, trajectory planning, and then stable flight control. In a UAS, they can use their local sensors to observe landing sites when they're in sensor range, but sometimes landing sites may not be immediately available. And because of that, there has been significant research into using onboard maps, landing site selection, and for path planning. Many propose to use offline geographic information system data for this map creation process. This includes satellite images, airborne lidar point clouds, digital elevation maps, building outlines, numerous GIS data sources. However, most of this work focuses on terrain-based landing sites, which are conventional, like open fields, open grasslands, maybe empty roadways. However, oftentimes when you're in dense urban cities, those just aren't available. Like consider this rooftop on the right. Ella's here. I'll just pause a second. Ella, thanks for joining. I had just started the presentation. Are you there, Ella?
Yeah, I'm there. So I see that you've started. That's awesome. Welcome, everyone. Please continue, Jeremy. My internet is now stable.
Okay, awesome. Thanks. But like I said, consider the satellite image where there's not a lot of options. But what you do see are numerous unoccupied flat rooftops, and which we are going to propose to use as those can be alternative landing sites in dense urban cities. But the thing is, rooftops are not always empty. Rooftops often have skylights, rooftop entrances, AC units, and you need to be able to account for that. And this dissertation is going to talk about using polygons to accurately describe these surfaces, as well as the obstacles that are embedded upon them as well. So our problem statement, this brings us to our problem statement. Where can a small UAS safely land in a city during an urgent or emergency landing situation? How can maps be constructed and risk evaluated for landing site selection and path planning? And how can a small UAS verify a landing zone is safe in real time on approach to that site? Now, the primary themes that bring together my entire dissertation is the concept of identifying flat rooftop buildings, representing their flat surfaces as polygons, and finding risk minimum touchdown points for those surfaces. Now, to answer those three research questions, I decomposed that work into 7 different tasks. And those tasks are distributed against 6 chapters in my dissertation. Now, for the first task, our first task is to efficiently extract non-convex polygons with interior holes from 2D point sets. And this is in chapter 2 of my thesis. The next task is to extend this work from 2D to 3D data, where the polygons represent flat surfaces and interior holes represent obstacles embedded on that surface. In chapter 4, I do my third task, which is to classify rooftop shape in a city, for example, if it's flat, using machine learning with high confidence in our model prediction. Then for tasks 4 and 5, they're both going to be in chapter 5 of my dissertation, and it's about using the data and the work I just talked about. So we're going to assimilate publicly available GIS data, such as satellite images, airborne lidar point clouds, and existing map data into an urgent landing site database that includes building rooftops. And this database is going to be risk evaluated, so we'll have the riskiness information, as well as have 3D maps for path planning. And for task 5 in that same chapter, it's about using that database. We're going to create a multi-goal planner that can search through multiple different candidate landing sites that might be around us, and trade off between landing site risk as well as the flight path risk towards those sites. And then for tasks 6 and 7, we are talking about using our onboard sensors when we're above that rooftop to verify a touchdown point in real time. And so for chapter 6, for task 6, we'll test out this work in simulation, while for task 7, we're going to do real-world flight experiments showing and demonstrating this work. Now, there are a lot of contributions and innovations between these 6 chapters in my dissertation, but these are the most important ones that I wanted to express. That we've created an efficient and very versatile open source framework that we call Polylidar 3D that can extract non-convex multi-polygons from 3D data. We have multiple open source and reproducible experiments showing Polylidar 3D working with numerous different types of sensors. And we also present the first large-scale multi-city analysis predicting roof shapes, and the provided annotated data set contains diverse examples from small to large metropolitan city centers. And we also present for our emergency planner a multi-goal planner that can guarantee a risk-optimal solution is found that balances landing site risk and path risk. And the thing that kind of ties everything together is that this is the first rigorous method to incorporate flat rooftops for candidate landing sites for urgent landing of small UAS in cities. And then finally, we have some flight experiments showing real-time touchdown point selection. Now, there are 6 chapters in my dissertation, and there's no way I'm going to be able to go into detail over all 6 of those chapters. And because my dissertation committee has already seen actually most of this work, I will be summarizing the work for chapter 2, chapter 3, and chapter 4. So first, for chapter 2, the problem statement is that we want to extract the shape of a 2D point set as a polygon. And now there are a spectrum of the type of polygons that you can do for this task. For example, consider this point set on the left that has the letters, the shape of the letters AI. You can extract a convex polygon, shown here in red. And this is a very computationally efficient algorithm to do it, but it does overestimate the area of that point set. You can then also do a non-convex polygon, shown here in green, where you can see that linear ring of the polygon is more closely conforming to the shape of that point set. However, you will notice that there's a glaring gap in the middle of the A, where it's completely unaccounted for in this representation. And then the representation I use that I like is non-convex polygons with interior holes, where you have an explicit representation of the exterior boundary of that point set, the shell as shown here. And then also you have linear rings that are denoted orange, which are the interior holes within those polygons. Those are those gaps that are in the point set. So I created the algorithm for this work called Polylidar, which will take a 2D point set and create a non-convex multi-polygon with holes. Now, I'm not the only one to create an algorithm like that. There are competing algorithms like CGAL alpha shape, spatial like concave, and PostGIS, to name a few of them. But to kind of summarize the results of this method in my work, that my work was shown to be 4 times faster from point to polygon compared to other open source alternatives. And the speed is attributed to its very efficient region growing and boundary following procedure instead of doing alternatives like computationally expensive unioning of triangles repeatedly. Source code is fully open source available and was tested out by reviewers and even by myself. And also the paper is available also from IEEE RA letters as well. And now we're going to talk about moving from 2D data to 3D data. So flat surfaces are very pervasive in engineered structures. We're talking floors, we're talking walls, ceilings, rooftops, and sensors like RGB cameras or LiDAR sensors can generate dense 3D point clouds of these environments. In robotics, there are a lot of tasks like localization or mapping or point cloud registration that are very interested in those flat surfaces. And so they use a technique that's very common is use planar segmentation, which will be able to identify those planar surfaces. So for example, there's the peak algorithm, it's shown on the right, that'll take an RGB image and it segments the ground floor as red and then also the wall as yellow. And that's an example of plane segmented point clouds. Now, plane segmented point clouds are wonderful, but they have some drawbacks. They're very memory intensive, and which could also lead to computational extensiveness too, because these could be tens of thousands to hundreds of thousands of points. And so there's been some interest in the robotics community to convert these to lower dimensional representations as well, like polygons. There's been some work with convex polygon extraction and also with non-convex polygon extraction. And you can see an example of that on the bottom right for convex polygons. However, nearly all of this work always assumes an organized point cloud, like an RGB image. In addition, there was missing work with non-convex polygons with interior holes. And that's what I was interested in. So I wanted to solve that. I wanted to fix that. So I made something called Polylidar 3D. And so this is an overview of kind of like the software and how it works and the entire framework. There are 4 different steps of it. Basically, we have our data input, our front end, our back end, our output. Now, the data input, we continue to still take 2D point sets as before, but we can also now take unorganized 3D point clouds, organized 3D point clouds, and also user-provided 3D meshes. And then our front end will take each of these different data inputs and then convert it to a half-edge triangular mesh form. That becomes a common level of abstraction such that the back-end core algorithms can then operate on. And the core algorithms have mesh smoothing, dominant plane normal estimation, the planar segmentation, and then the polygon extraction. And then the output of my software, my work, creates something called the planes and the polygons. And the planes is the exact same thing what we would give out, just these large planar segmented point sets. But we also present the polygonal representations, which you can see in the very bottom right image, where you can see the ground floor has been captured as a polygon, but then it also captures the obstacles of my roof, not my roof, sorry, of my chair. And also, I think that's a kettlebell that's on the ground. And so everything that's highlighted in red here, that's all my own work. That's the stuff that I created, my methods, my algorithms to do that. And all the other items that you're seeing that aren't highlighted, those are work from other open source software that I just pulled in, or I read papers, and then I just created the efficient software to actually implement those algorithms. Since this is a summary of this work, the basic idea of how the method works is that we estimate all the dominant plane normals in a 3D scene very quickly and efficiently. The triangles within the mesh are then grouped according to these dominant plane normals, and then region growing occurs in parallel according to planar constraints specified by the user. And then polygons are then extracted for each of these planar mesh segments. And then what's really interesting is that we utilize both data and task-based parallelism. This means that planar segmentation and polygon extraction can actually occur in parallel if you have CPU multithreading. We evaluated all this work that I did on 5 different experiments. These are completely different data sets. We had 2 experiments with real-world unorganized 3D point clouds, like driverless LiDAR point clouds, as well as airborne LiDAR point clouds. We had 2 experiments with organized 3D point clouds, and then 1 experiment with user-provided meshes. Because of lack of time, I can't show you all these reproducible experiments, but I'm going to show you, I think, the one that is the most telling. So this is a benchmark data set evaluation I'm doing. It's with SynPEB, which stands for Synthetic Plane Evaluation Benchmark. And it's a really challenging benchmark. It was just released in 2019 too. The data are organized point clouds of laser scans with a variety of different noise levels. And you can see in the picture on the top right of example one of these laser scans in the ground truth segmentation of what you're supposed to be able to predict. On average, there are about 42.6 planes within a scene, and sometimes you can have 72 different planes. So this makes it a very, very challenging planar segmentation benchmark, especially because there is copious amounts of noise within the data. There are some common metrics, evaluation metrics, that the academic community has settled on for planar segmentation. They're the header on the table that's down below. The ones I'll explain are F%, which stands for the percent of planes correctly segmented. So if there are 40 planes in a scene, you get 20 of them correctly, that's a 50%. And then K% is the percent of the point cloud correctly segmented. You can think of that as F%, but weighted by the size of the planes. Then there is NO, NU, NM, and NS, which stands for the number of over-segmented, under-segmented, missing, and spurious planes. You want this all to be low. You can think of all those numbers as a very fine-grained stratification of false positives and false negatives. And then we have the results. And so we compared with Peak, MLESAC, PPE, and Polylidar 3D. And PPE was the state-of-the-art forerunner for this benchmark set. PPE stands for probabilistic plane extraction too. So you can see on F%, it still is the best. It hasn't changed. It got 73.6% of all the planes correctly segmented, which is honestly quite extraordinary because of how difficult this challenging benchmark data set is. And Polylidar came in second. I only got 47.3% of the planes. But then when you look at K%, the percent of the point cloud correctly segmented, you see that Polylidar came in the best, the top. And this is because it's extracting all the large dominant planar surfaces that are in the environment. And if CPP is lower than Polylidar 3D, that must mean it's missing many of these dominant planar normal surfaces, which means it's trading off the ability to capture the larger surfaces in order to catch the smaller surfaces that might be in the environment. And then our plane fit error is also lower, as well as the number of over-segmented, under-segmented, and spurious planes. And those metrics are also just equally important because You don't want an algorithm that just blindly predicts planes that don't exist or predicts that there's two planes when there's only one plane, for example. And then another metric, which I personally think is really important, is the execution time. And you can see Polylidar took 34 milliseconds to perform this work, while PPE took 1.6 hours. And so I think what you can take from this work is that Polylidar 3D can do an excellent job at extracting the large dominant planar normals within surfaces very efficiently. And what's also really exciting about this work is that Polylidar didn't just extract the point sets, it also extracted the polygonal representations. And that execution timing is including that as well. So I'm actually doing even more work than just extracting just the point set representations. So into conclusion for this work, Polylidar 3D extracts non-convex polygons with holes from a variety of different types of 3D data sources. It's evaluated in 5 different experiments. They're all reproducible that you can evaluate. And we benchmarked against other competing methods for planar segmentation, and we showed to be quite fast and accurate at extracting dominant plane normals within scenes. The source code is available, and it's actually kind of used quite a bit on GitHub, and the paper is also available freely. The next work we'll be summarizing is work for roof shape classification, and we'll be using deep learning. So roof shape, such as a flat roof, is a very important feature of buildings. You can see some examples of roof shapes on the pictures on the right. This information is used extensively for urban mapping, 3D city reconstruction, solar panel placement, I found out, and what I'm proposing, alternative landing sites for UAS. Common data sources that are used to predict roof shapes are airborne LiDAR point clouds, digital surface models, satellite images, and even building outlines. Machine learning techniques have previously been used to try to predict roof shapes, and quite a bit. They have to use support vector machines, random forest classifiers, convolutional neural networks. If there's a machine learning technique, I guarantee it's almost been tried exhaustively with trying to predict roof shapes. But what's different about my work I'm presenting in this chapter is that almost all the published papers that did all this work, they focus on only one city, and they usually have very small test data sets. In contrast to that, this chapter in our work looks at 3 diverse cities: Witten, Germany, Ann Arbor, Michigan, and the Manhattan borough of New York City. And this allows us to see the generalizability of the model that we're using for prediction. In addition to that, we are fusing both satellite image and LiDAR data for improved prediction by the concept of using 2 different modalities to help improve prediction performance. This is an overview of what this final model looks like. Basic idea is that we have raw GIS data we're taking for each of these 3 cities. We're looking at airborne LiDAR point clouds, building outlines, satellite images. We pre-process all those information to create 2 images for each building, an RGB image and then a LiDAR image, which is basically just a depth image. And then we have independent convolutional neural networks that will extract high-level features from each of these different modalities. And then after those high-level features are extracted, we then concatenate them with each other and then send them to a random forest classifier, which will then give us a final roof shape prediction. Now, this is actually the final model. We tried out many different convolutional neural networks, many different classical machine learning algorithms, but through our validation set testing, this was shown to be the best for our work that was done in 2017. So in order to train, validate, and test data, you need a data set. And like I said, all those other prior work, they never had released any of their open data sets that they used for their training. And so I actually had to create my own, and so I made the world's largest one. So I looked at over 4,500 different buildings across 3 different cities, and I looked at about 9,000 images, and I labeled each and every single one of these rooftops manually. And so you can see some examples of some roof shapes that were labeled from the top. But in addition to labeling just the roof shapes, I did something else that was different. I also labeled whenever I saw malformed images or images that a model wouldn't be able to predict with. For example, if there was a satellite image that was supposed to be over a rooftop, but there was nothing there, it was completely empty. Or whether there's trees overshadowing a rooftop that leads to malformed LiDAR images because the LiDAR is being occluded by the treetops. Every single time those things occurred, I noted them and I recorded them during my classification and labeling. And the reason why that's important, you'll see, is that now the final model is actually able to handle malformed images from both satellite and point cloud inputs, meaning that it's a real-world, realistic accuracy results I'll be presenting where you can actually trust the output of the neural network because it understands when it sees bad data. It knows not to give false predictions when bad data occurs because I trained it how to recognize bad data. So to summarize this work, we had the largest annotated roof data set that was created with over 9,000 images. We achieved an 87% total accuracy across 8 different classes from 2 independent test sets. And if we are only interested in flat-like roofs, which is what I'm personally only interested in, we can get over 95% precision and 75% recall for all these flat roofs in cities, which is pretty extraordinary because before you had nothing. You had no information about flat rooftops, and now you can have an incredible amount of confidence in it and still get 75% of all the flat roofs that are within the city. The data set is open and available, and it's used actually quite a bit as well, and the paper as well. So now we're going to stop summarizing as much, and now we're going to start talking a little bit more detail about some of the new work. So now we're going to talk about creating a landing site database, as well as using a planner to choose which landing sites we should get to use. So prior work has used GIS data before to create landing site databases and occupancy maps for path planning. But what's different about this work is that our onboard database of maps is going to include rooftops. But in order to do that, you need to have roof shape, you need to understand how to extract flat surfaces, and you need to understand how to work with obstacles. Everything I just talked about in the last 10 minutes or 15 minutes gives me all the tools I need to accomplish that task. In addition, what's different is that we will have models that will assess the landing site risk of a site that can be done offline, but we'll also have models to assess the path risk online. And we're going to create a multi-goal planner that is going to show that you can trade off between those 2 different forms of risk. In addition, what I think is really exciting is that we can perform a multi-city analysis for urgent landing, where you can see how does your emergency planner affected, your performance metrics are affected when you switch from a city like Ann Arbor, Michigan to a city like New York City. How is your planner affected by such a drastic change in city makeup? And we'll have answers to those kind of questions in this work. So this is the basic idea of how you create these landing site databases and occupancy maps for path planning. We have our raw GIS data like LiDAR data. OSM stands for Open Street Maps. It's basically Google Maps, but free. And then satellite images are as well. We take all these data and we have these processing modules like roof shape prediction, which I just talked about, flat surface extraction, which I'll talk about in a second. And then we have this new one called touchdown site analysis, and then some landing site feature analysis. We'll run our data through these modules that I create, and they will generate a landing site database that will have all these different landing sites available, including rooftops. And it will also generate a 3D maps that we'll be using for path planning. So let's talk about landing site. So the pictures that you're seeing are of 3 cities: Ann Arbor, Michigan, Witten, Germany, and then New York City. And we still are going to continue having our terrain-based landing sites, the open fields, the grasslands. We're not getting rid of those. But what's new now are all these buildings that you're seeing with these crosshatches, the blue crosshatches. Those are all flat-like roof buildings that have been predicted by the machine learning algorithm. And you can see is that it's providing a wealth of new types of landing sites that you could possibly land within these cities. And you can see in New York City how important that really is, because there's not that many open fields and grasslands to land, but there are so many flat rooftops to use. However, we're not just going to trust the output of that neural network and just say, okay, it says it's a flat rooftop, blindly assume we can land there. No. What we're going to do is that for every rooftop that has been predicted to be flat, which uses 2 modalities, we're going to get the airborne LiDAR point cloud of that rooftop, shown here in the picture on the left. Then what we're going to do is we're going to use Polylidar 3D. It's going to extract the mesh planar segment of that rooftop, shown in the center image. And then we're going to extract the polygon as well. And that's shown as that orange polygon that you see in the 3rd image. And then finally, what we'll do is we're going to do a Polygon Post-Processing technique where we're going to buffer that polygon and simplify it. So the basic idea is you're going to constrict the outer shell of the polygon by, let's say, 0.5 meters, and you're going to expand outward the interior holes, which are the obstacles on the surface. This basically provides a safety buffer for the polygon for where you can land on. And then there's a reference satellite image on the right that you can observe as well. And you can show that it does a really good job of extracting and finding that rooftop and all the landable surface area. In addition to that, we want to go even farther. Not only do we want to know the flat surface, we want to know exactly where on that flat surface are you going to land on that rooftop. And to do that, we're going to find the largest inscribed circle in this polygon using something called the polylabel algorithm. And the basic idea is, you can see the output on the very far left. You'll find the largest inscribed circle, and that center of that circle guarantees that that point in that polygon is the farthest away from any exterior edge and any interior hole. And so that's the best place to land for that rooftop. And then what I do is I create an algorithm that basically iteratively fills our polygon with these ranked touchdown circles. And it basically will halt when a minimum radius can no longer be found within that polygon. And so this picture on the far right, these are all the best places to land on that rooftop, all ranked accordingly to their size. Now we're going to talk about landing site risk and how we're going to evaluate all these different landing sites about which ones are better to land on. So this has been discussed extensively in aerospace emergency landing research. And one thing, we're going to use the model that someone else has come up with that's been tried and true, worked really well. And it's shown in that first equation that you see here, where landing site risk, or RL, is composed of three terms. It's the cost to the vehicle, it's the cost to property, and it's the cost to human occupancy. And what's different about my work that I want to focus on is the cost to the vehicle, because I'm approaching that differently than other people have done before. And so we can see the very bottom equation, that is the composition of that cost. For the cost of vehicle is going to be a weighted sum again of the cost of the terrain type, what type of terrain it is. And then we have an area cost and then a cumulative area cost. And it's these two terms that I do very differently than other people, and I want to talk about a little bit more. So before, if you had a landing site and you wanted to assess the riskiness of it and you were doing it by area, what people used to do is they would look at that polygon at the bottom left that you see here. You would have that polygon that represents the landable surface is the blue and obstacle is orange. And to assess it, the area for risk, you would look at the full polygonal area of that polygon. The problem with that is that the areas in the top left of that polygon are completely unusable. So why are we including that area to demonstrate demonstrate the reduction of risk when it actually performs none of those functions? And so what we're doing that is differently is we're only using the usable space for the polygon, and that's the area that's actually calculated for each landing site, which is that primary touchdown circle that we talked about before. In addition to that, you could have rooftops, for example, that look like this, where they both have the exact same primary touchdown surface area. The building on the right, all things being equal, you'd rather land on it because it has alternative touchdown sites as well. And so we can capture that with the other metric we call cumulative area cost, where we sum up and add up all those ranked touchdown circles. The basic idea of this work is that we only want to capture usable landing site space, and we want to be able to discriminate between different landing sites that have more alternative landing sites on the same exact surface. So now that we're done with landing sites and talking about evaluating the risk for them, let's talk about path planning and how we're going to assess risk of paths. So in our maps, we're going to create 3D discretized grids of our cities. And the cellular size of our cities is going to be 2 meters. And you can see a picture of that in the picture on the right. And so this is a rasterized grid of the entire city of Manhattan, but you'll notice that it's been cut off at the top. So anything above 400 feet has been cut off, and that's because the FAA states you can't fly above 400 feet for SUAS. And so all the orange cells you're seeing, those are obstacle cells. And then what's surrounding those obstacle cells is a potential field of risk. And there is a stratification of different colors indicating different risks, like light blue, light pink, and then dark blue. Then for our path planner in this 3D discretized grid, we'll use A star, which is an optimal planner. And the heuristic we're using is the 3D octile distance heuristic, which is more efficient than using Euclidean distance when you're operating on a 3D grid. We use the standard equations for A star, nothing crazy different. And then here's a simple example animation of what 3D path planning looks like in this environment. And you can see that the open, you're actually visualizing the frontier and the closed set of the path planner. And you can see that it's doing a really good job with that heuristic of efficiently guiding the search space towards the landing spot. A couple things about this environment to note: you're not operating in a maze. That makes A star maybe more difficult. You're operating in open airspace. You might be maneuvering around buildings, but you're not in a maze. And number two, we're not traveling really long distances. We're interested in landing sites that are immediately nearby us. We're interested in distances less than like 250 meters. So all these attributes of our domain for our problem make it very amendable that A star can be performed very quickly in such environments, sub millisecond basically. Now here is an example of of how we're going to choose landing sites. So let's say we're on the picture on the right. The position of the UAS is in the center of that circle. What we're going to do is we're going to search a radial footprint around us of places that we could land. So the circle represents our search footprint for different landing sites. And then we search our database using a spatial query, and we'll get back the available landing sites near us, which are denoted those green circles that you're seeing. And then there is a path that you have to do with a path planner to get from your current position to those landing sites. And then we can assess the path risk of that path by using the path length plus any penalties that come from the potential field that you might be crossing. And then we normalize that by the radial footprint. So path risk will be somewhere between 0 and 1 generally. And so our objective is to find the landing site that minimizes the intrinsic landing site risk of that site, as well as minimizing the path risk in order to achieve to get to that site. That is a multi-objective optimization problem. Now, to solve that, what we do is we perform a weighting factor between those two objectives, and then which creates a new metric we call total risk, or RT. And so our objective is to find which landing site of all the landing sites around us in the radial footprint minimizes our total risk. There's a frustrating problem with solving this optimization problem, is that you need the path risk, which means you need to do path planning. And I know I just told you a second ago that I can do path planning very fast, and I can. But spoiler alert, there can be over 300 rooftops around you. And doing 300 path planning problems is very expensive, even though I can do it fast. And so what we want to do is we want to prioritize our search. And how we're going to do that is we're going to prioritize by minimum total risk. And the minimum total risk is basically just the total risk, but instead of actually doing path planning, we just use the heuristic in the path planner to give us a lower bound of what that path risk would be. By having that, we could then sort our landing site list of all the different landing sites that could be there. And then we can perform path planning starting at the first index and getting the true total risk. In the dissertation, we present a theorem as well as a proof that shows that there can be a halting condition that when you find a true total risk that is less than the minimum total risk of any other landing sites that have yet to be searched, then you know you have solved the optimization problem in the bottom left. Basically, the minimum total risk, once you find it, once you can guarantee it's less than the minimum total risk of other landing sites, you're done. And so with that, it can become very efficient and fast at finding and solving the optimization problem. Here are some examples of what this looks like in cities. So this is an example of Witten, Germany. So the position of the UAS is shown in green, that's in the center. And then you're seeing a bunch of landing sites distributed around that UAS. And they're denoted as those colored polygons from light yellow to dark orange, representing low risk to high risk. And then you have these blue circles. Those are just the actual touchdown points for each of those landing sites. If you were to plot the landing site risk and the path risk for each of those landing sites, you would arrive at the graph on the right that you see, where each of those purple dots represents one of those landing sites on the left. This also creates a set called the Pareto frontier, which is shown by that green line. Every single purple dot on that green line is technically optimal. They're all optimal choices to choose, but you can only go to one. You can only choose one landing site to actually move to go to. So that's why we have that weighted trade-off between the two objectives. If we were to set them equally weigh both landing site risk and path risk, you would arrive at choosing that red dot, which corresponds to that marker that you see in the map. The reason that's chosen by the multi-goal planner is because it sees that a very, very small increase in landing site risk had a drastic decrease in path risk. And so you see that elbow, that classic elbow shape that you want to see in a Pareto frontier, where it's going to choose the element or the landing site that's on that elbow. And that's why the multi-goal planner chose that landing site. And it's actually the fourth best landing site in the entire area of all. I think there's like 80 or 90 landing sites there. So it did a very good job choosing even a low risk landing site. But in addition to case studies, we also did Monte Carlo simulations, where we chose 500 random failure positions within these 3 different cities. And then we calculated the planner performance metrics. So the metrics are how many landing sites are available for you in a 250-meter radius? How long does it take to query the database to find those landing sites? That's a spatial query. What's the planning time, including the path planning time, in order to choose which is the best landing site? And how many how many times did you actually have to do path planning in order? Like how many times did you have to actually do path planning to verify you found the optimal landing site and path pair? So if we look at the image on the top left, this shows you the number of landing sites. And I think the most interesting thing you see is that there can be over 323 landing sites surrounding a drone in New York City. That's because of all those flat rooftops that are available. But on average, there's around 60. And then for Witten, it's around 50 landing sites. And then in Ann Arbor, there's around 30. And it's important to note that there will always be at least one landing site. And the reason I know that is because I did a statistical characterization that 250 meter radius guarantees you'll find at least one landing site in each of these cities. And then if we look in the picture on the right, this is the database query time. And we use a very efficient spatial indexing for our spatial database. And so everything takes less than 2 milliseconds to find all the landing sites around you. And then when it comes to the path planning time, including the multi-goal planner, you can see that the maximum time it ever took was 166 milliseconds. And so that's in New York City. And that's just a testament of the power of using good data structures, good heuristics, and using that heuristic of sorting prioritizing search by that minimum total risk. And so to kind of conclude most of this work, this is the work that incorporated flat surfaces of rooftops into a landing site database. And we could determine and rank them by usable landing site area. We balanced landing site risk and path risk metrics, and we performed multiple case studies that visualize those different trade-offs. And then finally, we performed hundreds of simulations experiments in 3 different cities to statistically characterize our planner's performance. All of these are really strong research innovations as well. So the next thing we're going to talk about is about when we arrive to a rooftop, what are we going to do? How are we going to use our onboard sensors? So like I just talked about, we just did the map-based planner. Let's say we find a rooftop that's near us. We have a proposed landing site rooftop. We have a proposed touchdown point on that rooftop and a trajectory. We trust it. We navigate our drone, and now we're above a rooftop. What do we do now? Well, we just blindly trust this map's prediction of where to land? No, generally not. You're going to use your onboard sensors. You'll have some type of sensor-based or perception-based planner. We'll be able to verify a landing site and do touchdown point selection in real time. And usually the sensors you're going to use to do this could be LiDAR sensors or vision sensors for SUAS landing. Now here's some background about how other people do real-time touchdown point selection using onboard sensors. If you're using monocular cameras, which is very prevalent because it's very low cost and lightweight, a technique that I've seen is use canny edge detection. One sec. The basic idea is you have a top-down image of some area you want to land at. You use a canny edge filter, and that finds all these lines that represent differences and changes in texture. And then what you do is you do random sampling of points within that image. And then you go through each and every single one of those points, finding the point that maximizes the distance between any edge found in that canny edge filter. Now this works well and it's pretty nice, but there are some drawbacks. You are doing random sampling. There's no type of optimization with this. In addition, it relies upon the assumption that homogeneous textures equals planarity, which that assumption does not always hold. Another technique that I like a little better is to use structure from motion, where you'll take multiple monocular frames over time to create a 3D point cloud, and then you can cast that point cloud to an XY ground plane to create an elevation map or a disparity grid. And then you basically have pixels that describe the planarity of the surface, and then you perform smoothing, usually Gaussian smoothing on that surface, and then you search for the pixel in that rasterized grid that has the best characteristics, the best thing that indicates planarity. The flattest pixel, I guess you could say. Another technique of using LiDAR sensors, which is really new and interesting, is you do point region growing and plane fitting. You have this huge point cloud, you go through all the points and you do region growing and plane fitting, and then you arrive at an image on the right where basically you've classified different points that are suitable for landing. So all the yellow points, those are suitable points for landing. And then to choose where to land on those yellow points, you go through each and every single one of those yellow points, and you find out which one has the best characteristics, which one's the flattest in the area. So in contrast to that kind of work, what I was interested in accomplishing was to continue to describe landing site surface as polygons. And so polygons represent continuous bounded space. This is in contrast to discrete space, like all those methods I talked about, whether you're in image space, rasterized grid space, or hundreds of thousands or millions of points. And in addition to that, I'm interested in optimizing on a touchdown point based on our distance to obstacles. So the polygon represents minimum planarity, which you specify using geometric constraints. And then I search within that continuous space using computational geometry routines very efficiently to find where in that polygon is the best place to land. In addition, what's different is I'd like to introduce a neural network into this polygon extraction technique such that we can use some semantic information as well as just geometric LiDAR information. And so that last bullet point, I'll be getting to that in a couple of slides. Before I could actually start doing any of that work, I need an environment to test things out. So I wanted to make a simulated environment. But before I can make a simulated environment, I need to know, what do rooftops really look like? What is actually on rooftops? So what I did is I analyzed over 100 rooftops in Manhattan. And I looked at satellite images, which you can see at the top, and airborne images. And I even looked at LiDAR point clouds. And then I painstakingly observed and noted every single thing that was on those rooftops. I literally spent hours, days, counting the AC units, how many there were, air vents, rooftop entrances, you name it. I noted everything I saw on those rooftops. And I created a data set that describes those rooftops. And that allows me to create a histogram, a statistical distribution of what things are actually on rooftops. So I guess, surprise, surprise, the most prevalent thing are air vents. You need a way to vent off all the hot air that accumulates in the roofs and buildings. And then also small rooftop entrances, because you need access, maintenance access to rooftops, as well as skylights as well. And so basically what's going to happen is I'm going to use this information, these distributions, to inform me when I create my virtual 3D worlds, that I will build worlds according to these distributions that I learned from my analysis of Manhattan. Speaking of the simulated worlds, I decided to use the Unreal Engine for my simulated environments. So Unreal Engine, if you're not familiar, is a AAA game engine. So it makes video games, but it can also be used for robotics. There's no reason not. And you can see an example of the cities that I made, like how it looks in the top right picture. You can see the different types of buildings, their shapes and their heights. And then the bottom right picture, you can see an empty world that I created where all the rooftops start off empty and there's nothing on them and what they look like. And then what I did is I personally purchased many assets from GameStorms from the Unreal Engine marketplace. So I purchased air vents, AC units, water towers, all these things. And then what I learned is I learned how I can modify. I learned game programming. I learned how I can modify those actually assets so I could configure all their special properties like their textures, their reflectivity, and I could dynamically manipulate those properties to create randomness and diversity within my cities. And I could make really interesting complex changes as well. And then what I did is I created something called a world generation script, where I took a map of my city, I took all the assets and their configurability, and then I took the histogram distributions of those assets that I talked about for Manhattan. I combined them together to create new virtual 3D worlds that basically place these assets on many, many different types of worlds according to the distributions that I had from the Manhattan data set. And now that I have these nice new random worlds that have these interesting assets on them, I need a drone, right? I need a drone to fly around these worlds to do touchdown point selection. So I used a plugin called AirSim, which is made by Microsoft, which allows me to have drone and sensors. So I'll have a LiDAR sensor and a camera sensor mounted underneath the drone that it uses for sensor-based input. Now that I have this world, I can start formulating some ideas for some methods. And so this next slide is talking about my motivation about why did you want to start using a neural network with Polylidar 3D? Why did you want to do that? Well, LiDAR with my computation geometry, my software, is really awesome. It has some great strengths. It is very explainable and very well understood. All the computational geometry algorithms are. There are explicit quality guarantees. I guarantee you a valid polygon. I guarantee you certain planarity constraints according to that polygon. So it's nice to have those explicit guarantees, especially when you're dealing with safety critical decisions like where you're going to land in emergencies. And also my software specifically is very resource efficient. It has very tight, a tight envelope on the computation and memory bounds. But at the same time, there are some incredible strengths for deep learning, like you can't discount it. It has all the state of the art in accuracy for numerous different computer vision tasks. It's the top leaderboard always. It's extremely parallelizable, not just in CPU multi-threading, but for GPU acceleration and even for ASICs. And it also has very fast-paced progression, which is really important because even if you're taking 1,000 tiny small steps, but as an academic community, you're going to arrive at a mile every single year, even if you're taking small steps. And so you can make some incredible progress that's been shown just in the last 3 years in this endeavor. And so at the same time, there are also some drawbacks, some negatives. So with my work, computation geometry, a lot of work I did, there could be some really small, brittle failures that are actually quite disheartening to me, where if a triangle does not meet the planarity constraints, it is not included. There's no ifs, ands, or buts. It's not included to keep those requirements. And it doesn't look at global context that a human would to understand there's no reason, that's just noise in the sensor. Continue to clean it. It doesn't matter, it's gone. And at the same time, there can be weaknesses with learning. You can have very hard failures sometimes. This usually happens when you see data you've never seen before. Like obviously the way the neural network works is you train on data, but you can't see all the data in the world sometimes. And sometimes you see things you weren't prepared for, and the output of the neural network can be complete junk sometimes. And there's also issues with adversarial input as well. In addition, there can be very high memory and computation requirements, especially specifically for all the that I've been noticing for many of the state-of-the-art algorithms I see. It just seems like more of the models get much more denser in the parameter space. So I was interested, is there a way to kind of simply combine this work together so that we can remove some of the weaknesses that I had with Polylidar 3D? And so that's what I made. It's called Semantic Polylidar 3D. And it's called semantic because it uses semantic segmentation. Basically, you'll have an input image on the left that's downward facing from the camera of the drone. And then you're going to go through a semantic segmentation neural network with an encoding block and then a decoding block. And eventually it outputs a semantic image on the right. And basically, each pixel has a class label associated with it. So that's like the rooftop class. You have different types of classes that you can see. And so I'm interested, can I use the image on the right to help make my polygon extraction better? And so in order to do that, though, I first need those semantic segmentation neural networks. I need them. So I coordinated with a colleague of mine, Dr. Brian Yao. He just graduated just recently, really exciting. And he proposed that we use some very lightweight semantic segmentation neural networks, like MobileNet or ShuffleNet. These are networks that can work really well at predicting a semantic segmentation image, but do it without as much computation overhead and memory overhead. In addition, we gathered over 16,000 images for training, validation, and testing to train these different networks. And he did all this work, Brian did, and then we arrived at basically MobileNet and UNet being the best combination to use for our semantic segmentation images. So it can basically, that'll be the network I use to create the images that you're seeing on the bottom right. Now we're going to talk about how you're going to use those images with computational geometry. So you start with an image on the left, which is just an RGB image. You perform semantic segmentation, arrive on the image on the right. And then what I did is I project the LiDAR point cloud into that semantic image such that each point now has a classified label associated with it. It's now a classified point cloud. And then I convert that classified point cloud to a half-inch triangular mesh per standard procedures with Polylidar 3D. But now the mesh has classified vertices. And you can see that in the image here. The green vertices are the rooftop class, orange vertices are some obstacle class, and the blue vertices correspond to an unknown class. This can happen if the field of view of the LiDAR is greater than the camera, such that the points do not project into the image, and so you have no class labels. So now the point is, how can I use this classified mesh to do a better job of region growing? And so what I decided to do is basically loop every single triangle that belongs into that mesh. And so that's where there's K triangle this mesh, we're looping through each one. For lines 4 and 5, we're getting geometric information from that triangle. So this is like the maximum triangle edge length. This is the angular deviation from the dominant plane normal of that surface. And then lines 6 and 7, that gets semantic information from that triangle. We're counting the vertices that belong to the rooftop class and counting the vertices that belong to this some type of unknown class as well. And then in line 8, we create semantic constraints, basically, where if the number of vertices and unknown vertices is less than, for example, it's greater than 2, then we pass semantic constraints. So basically, if we have enough vertices that we're confident with that belongs to some certain class, then we can pass our semantic constraints. And then in lines 9 through 12, we're doing something a little interesting where the basic idea is that if we have a high confidence that this triangle belongs to the rooftop class, then we can reduce the angular geometric requirements for the computational geometry requirements. So basically, the confidence in one modality can reduce the confidence required in a different modality. It doesn't remove the other modalities requirements, but it just you can reduce it. And then in lines 14, if semantic constraints and if geometric constraints both pass, then and only then do we include the triangle to be possible for our computational geometry polygon extraction routines. So this is a way that allows us to kind of simply find a way to kind of merge both of this information, both geometric and semantic information, but very fast and still very efficiently, because speed was important to me, but still having the ability to kind of have both these information part of the region growing procedure. So afterwards, you do standard Polylidar 3D work, you extract the polygon, and you find the touchdown point that maximizes distance to obstacles. And so now the question becomes, how effective was that? How effective was it? Well, it was really effective, actually. So here's an example of a semantic image on the left, and then here's an image on the right is a monocular camera image. And then you're going to see the projection of the ground truth polygon of the environment. That's the dashed purple lines. Those are the ground truth. And then our predicted polygons as well. Those are the green lines as well as the orange lines for the obstacles. And you can see that it did a really good job of finding in real time where to land from this environment using using the laser scanner and the semantic image. Here's another example I think is interesting. This is an example of semantic Polylidar 3D succeeding really well, even though there were failures in two different modalities. So let's look at this picture on the top left. We're looking down at a rooftop. There is a rooftop entrance, and there is also a tarp on the rooftop. And you can see a side view of that rooftop entrance as well. It slopes down near the front. The rooftop entrance texture is similar to the rooftop. It's not the same, but it's very similar. That causes a semantic segmentation failure on the neural network. It wasn't able to discriminate between the rooftop surface and the rooftop entrance because the texture was similar, and so it failed. This happens sometimes in neural networks. And so when that happens, because this is a hybrid algorithm that looks at both geometric and semantic information, semantic Polylidar 3D succeeded. It did not fail because you had the LiDAR data to back it up. And so you can see the orange line is completely encapsulating the dashed purple line in the center, which is that rooftop entrance. In addition to that, the semantic image captured the tarp correctly as well. Because it captured the tarp correctly, it also captured the tarp correctly in the polygon in the bottom left for semantic Polylidar 3D as well. It captured it perfectly fine. However, if you were just using LiDAR information, it would fail at capturing that tarp. The reason why is because there's range noise in the sensor, and the range noise was so high that it was hard to discriminate between the tarp and the planar surface of the rooftop itself. So this is an example where we had two failures. We had failures in range noise from our LiDAR. We had failure in vision with our neural network as well, but we had complete success with semantic Polylidar 3D using the strengths of both of these methods. So it's important to note that this worked. It worked because the failures occurred in disparate regions in space, in 3D space. If they occurred in the exact same space, there also would have been a failure. But because they occurred in different spots, it was okay. So here's some quantitative results of how this worked. So we looked at 33 different buildings, and we did 10 tests over each building. Basically, we're looking at different configurations over the buildings, different vantage points. And then we calculated the intersection over union of the predicted polygon versus the ground truth polygon. That should have been, that was the correct one. And we compared it with semantic Polylidar 3D versus just using a baseline Polygon Polylidar 3D method. And you can see it did substantially better, that we had a 91.2% for our intersection over union compared to only 86.8% for baseline Polylidar 3D. And we also presented a student t-test that basically shows that, yes, there is a statistically significant difference between these two different methods. The execution time was, because it's also important how fast you can do, was also very fast. It takes about 30 milliseconds to do this for every single scan. But most of that work is dominated by the neural network. And there's a lot of work that I should be doing, that I can be doing in the future to make the neural network faster. We could be quantizing the model. We could also be reducing the number of classes that it predicts as well. So there's a lot of work I think we could do to bring down that execution time as well for the neural network. Kind of to conclude this work, we've constructed a high fidelity visual city model from real world data of the rooftop obstructions in Midtown Manhattan, New York. And we presented a hybrid algorithm for planar extraction that accounts for semantic information using deep learning, as well as computational geometry. And we present a novel method for finding optimal touchdown points on rooftops and a processing pipeline that is shown to be viable for real-time deployment. All the code, the environments, the data of the rooftops is all open source, it's all available, and you can find it in the link there below. The next work we're going to talk about is some real-world flight experiments. That's the last chapter. So, previous chapter I just talked about, that was simulation work. It was camera and LiDAR data we're talking about. This work is going to be real-world flight experiments, but we're only going to use LiDAR only this time. But we're going to actually be integrating multiple frames over time to attenuate the noise of the LiDAR sensor. So in order to have real-world experiments, we need a sensor package. And so I created one here that you're seeing. It has a RealSense L515 solid-state LiDAR. This is a new technology of LiDAR data where it's very, very precise, and it also is very dense. And you can see it has about, I think, 2 millimeter, 1 centimeter accuracy, and it has about 10-meter range. So it has not really large range though. We also use a RealSense T265 tracking camera. This will provide our pose information. This is our position in space as well as our orientation in space. Basically, it's an onboard SLAM algorithm onboard that tiny little camera, which is really fascinating, really cool. Then we have an Odyssey x86 single board computer for our companion board. And then we have a 12-volt battery pack for our power. We're going to put the sensor package underneath the drone, which is mounted underneath, as you can see below. And the drone will be a quad rotor, the M330 quad rotor that was designed in the HSS lab. Our flight controller will be a BeagleBone Blue, and you can see it highlighted as well. And we'll be using a motion capture system. And you can see the motion capture markers on the drone itself. The motion capture system gives ground truth position information to the flight controller. And so it'll be used for all position feedback and all control commands. But the sensor package never gets the ground truth information. It has to do everything on its own using that T265 sensor. And then we'll have independent power sources between the companion board and the flight controller. And we will communicate landing commands. So the sensor package is in charge of finding touchdown points and communicating landing commands to the BeagleBone using a serial connection. So what is our environment going to look like for testing? We're testing in the University of Michigan Fly Lab. There are going to be 3 boxes in the environment and 1 ladder placed at very precise locations in the environment that are known. The flight area is limited to be a 1.75 meter square that's centered at the motion capture system origin. And the drone is going to survey this landing site in a box pattern that you're seeing here at about 1.5 meters in height. So the pilot in command will be navigating the drone in this kind of sweeping pattern so that the sensors can understand and see the environment to make a decision. The ground truth polygon of the workspace is on the right, and this will become the ground truth to assess accuracy. So I'm going to do my best to play the video and kind of briefly explain the entire pipeline. So the basic idea is that the drone has the LiDAR frame and the T265 data. We're going to temporally align that data. And then we're going to perform a process called volume integration per reference 30. The basic idea is that you're going to deproject these point clouds into 3D voxel space, and you make a truncated sign distance field. While the pilot in command is navigating this environment, we are continuously integrating the volume and creating this truncated sign distance field. After we've done scanning in the pattern that we talked about, we will then activate my urgent landing protocols, which will then extract the mesh, extract the touchdown point in the polygon, and then it will then create a trajectory to that touchdown point and then land. And that's exactly what you just saw in this video about it, finding a touchdown point and landing. And so here are some examples. Here are some examples of the meshes, the polygons, and the touchdown points that were created using this technique. You can see that it did a really good job of finding the boxes, finding the different ladders, as well as extracting the polygons and the obstacles that are embedded on those surfaces. It worked very, very well, all encapsulated in that tiny sensor package. In addition to that, if we project those polygons to the XY plane and then overlay them with the ground truth, you see the images on the bottom right, and you can see that it did a really good job at matching up with the actual ground truth of the environment, which is outstanding because there were so many different errors that could have occurred. Errors in the T265 sensors, errors in the volume integration, errors in the in the mesh extraction, in the polygon extraction touchdown point. But overall, it did a really, really good job. Quantitatively, the intersection over union of the polygons was 91 and 94% and then 92%. So it did a really good job with real world flight experiments of capturing that data. So kind of to conclude, final chapter, we did some flight experiments demonstrating real-time touchdown point selection. All 3 flights had a successful landing. All this work has open source hardware, diagrams, as open source software that can all be reproduced and shown online as well. So now to conclude my entire thesis of 5 years. So I guess the big thing I would say that I'm proud of is that this was really one of the first works that really robustly included flat rooftops into urgent landing site databases. And the guiding principles that guided me these last 5 years were to be as prepared, efficient, and lazy as possible. Prepared because I pre-processed as much data from as variety of sources as I possibly could in order to find landing sites and to assess risk. I was efficient because I tried my best to choose appropriate algorithms, data structures, and utilize parallelism as well. And I was lazy because I only wanted to perform work when it was actually required. There's no reason to perform work, especially in real time, when it's not needed to be done, just because it might be easier to do. And these principles guided me not in my publications, not only in my publications, but also in other contributions like open source libraries that people are using, as well as open source data sets, which people are using as well. And so here is a picture diagram of all the different journal papers, conferences, libraries, and data sets associated with this dissertation. And then finally, for future work, to talk about where I see as we're going in the future, I would be very interested in using 3D deep learning, which is a really awesome new techniques that I'm seeing right now in the last 3 years since I last looked at it, and I started looking last year, in order to segment airborne LiDAR point clouds. And then once I segment those point clouds, I can then send those segmented point clouds to Polylidar 3D to find the polygons. So I can use the strengths of 3D deep learning to properly segment them even better, and then use Polygon extraction techniques, which are robust and provide guarantees to find those rooftops. In addition, Polylidar 3D is used actually a little bit right now, but it's, like I said, it's meant for dominant plane normals. I'd like to make it better. I'd like to make it work for all different surfaces. But to do that, I need to modify the algorithm. And there's a technique that was just introduced last year called spherical convex hulls, which is awesome because it's exactly what I need, where it can make a very refined estimate of planar surface normals for even very small surfaces. So I'd be very interested in integrating that work into Polylidar 3D. And then I'm also currently doing work with autonomous wheelchair climb climbing. So I open source all of my work. Some people saw it from the University of Pittsburgh and they want to do a collaboration for wheelchair stuff. And so I've been doing that with Polylidar 3D, where they've been able to use it to find basically polygons of surfaces and curbs. And then we're able to find the correct mounting surfaces and the correct autonomous commands to navigate the wheelchair to align with the curb to mount it. And so I want to finish up some of that work. For acknowledgements, I want to thank Professor Atkins, Professor Starter, Ghaffari, and Stout. Thank you guys. Thank you so much for being a part of my committee, for listening to me, for supporting me for a lot of times. Especially sometimes I've struggled, and many of you have been there to support me. And you've also been my teachers as well. And you've taught me, and I've literally applied a lot of what you taught me as well. HSS Lab, Pedro, who is here too, Mia, Hossein, Cosme, Brian, Prashin, Matt, Prince, Joseph, Paul, Mark, Ann, John, and Sid, and maybe some others too. Thank you so much for being a part of the lab, listening to my crazy ideas and teaching me and helping me and being supportive. For flight experiments, thank you, Matt, John, and Prince. I never could have done those flight experiments, and Anne as well. I never could have done those flight experiments if you guys weren't there. I'm not a really hardware savvy person. I'm more algorithmically inclined, and because of you, I was able to put that work in my dissertation. Hackathons, thank you, Matt, Prince, and Prashin. We had the opportunity to compete in national and regional competitions and win first place for all of them. And it was exciting and it was wonderful. And I've made great friends with you guys. And I appreciate all the support you've given me, especially during those times as well. And then I want to thank my family, my mom, Didi, Megan, and then Natalia, Kiara, Emily, and Alan. Thank you. That's it.
Jeremy, that was wonderful. Thank you.